Hi, in this lecture I will give you an overview of statistical tools to quantify errors in your simulation data. Let us first define what a stochastic process is. Imagine you have a box filled with particles interacting with each other. You can define an observable A as the average thermal energy of the system. If your system is evolving through time, for every microstate omega available with probability P of omega, there is a corresponding value A of omega. Basically, the random process A is mapping a value omega to a value on the real number line. To be more rigorous, let us revisit this experiment using the notation in probability theory. The observable A can be modeled as a random variable, from which you draw values called realizations. If I read the short notation in the box, the random variable A is a function that maps values from the sample space big omega into the measurable space big E, such that for every microstate omega corresponds a value on the real number line. Random variables can be characterized by a probability distribution, and these probability distributions usually have two or more parameters. The most important ones are the mean, mu, and this variance, sigma squared. You can have probability distributions with more parameters, but usually the mean and the variance are the most important ones. The mean mu is a real value. It is simply the average of all possible realizations, which is, simply put, the integral of the random variable over the entire sample space, weighted by the probability of each microstate omega. The variance is simply the average of the square distances to the mean. These parameters, mu and sigma, are usually unknown, and you will need to estimate them using a small sample. Let us first look at a simple case where you have uncorrelated data. Imagine you would like to measure the radius of gyration of a polymer as a function of the number of monomers. For each polymer length, you will run multiple simulations with different initial conditions. Each simulation will give you one data point. You can consider these samples as uncorrelated. And so on the graph, for each polymer length, you can plot an estimate of the mean and an estimate of the error of the mean. You have a sample of independent realizations A1 to AN with n the sample size. The first thing you need is to find out the correct estimators for your statistics. The mean of the sample Mn is an unbiased estimator of the true mean mu. The variance of the sample Sn squared is a biased estimator of the true variance sigma squared, which means you will always get the wrong value. In practice, you will always underestimate sigma squared. Instead, you can use the sample variance Sn-1 squared, which is an unbiased estimator of sigma squared if and only if your random variable is Gaussian distributed. If you have a different probability distribution, you will have to look into the literature to find a more adequate estimator. This n-1 denominator is called the Bessel correction. The sample standard deviation is simply the square root of the sample variance. It is a biased estimator of sigma because the square root introduces a small deviation. However, this deviation is quite small for large sample sizes, in which case it is quite common to neglect it. This is due to the Jensen's inequality. We can now use these building blocks to create our estimators. What you have to keep in mind though, these estimators are themselves random variables. For example, the mean estimator M has itself a mean and a variance. And this is something that is going to help us. Let us first look at the estimator of the true mean mu. Estimators are usually written with the same Greek character as the parameter they are estimating, in this case the Greek letter mu. The hat symbol means it is an estimator. The subscript A bar means that we are estimating the true mean mu based on the average of the sample. In some textbooks, the hat symbol is removed because it is already implied when you write mu of A bar. Now remember, A bar is a random variable, and mu hat estimates its mean, but you still need to estimate the variance of A bar in order to create the error bars in your plot. The variance of A bar is simply the variance of the sample divided by n. If you expand it, you will see this n-1 appear. That's the Bessel correction. The reason is A bar converges in probability to a normal distribution in the limit of a large sample size. This is a consequence of the central limit theorem. Regardless of the probability distribution of A, the probability distribution of A bar converges to a normal distribution for large sample sizes. Please keep in mind that we are not trying to estimate the true variance sigma squared, which would require a different set of estimators. We are currently trying to estimate the variance of the mean, which is used to create the error bars on the plot. And these error bars will decrease in size as the sample size increases. Once you have the variance of the mean, the square root will give you the standard error of the mean, which is actually the quantity you will be using to create the error bars. Again, taking the square root introduces a bias due to Jensen's inequality. Let us now consider the case of a time series. In this situation, you can no longer assume that the realizations are independent from each other. Each realization will be slightly correlated to the previous one and the next one. And this correlation will introduce a bias that you need to remove. To illustrate the problem, I have here plotted the average thermal energy of a system of interacting particles where the temperature is controlled by a thermostat. In the first part of the graph, you see a steep increase of the thermal energy. That's the warm-up phase. And it is followed by a phase where the thermal energy is fluctuating around the preset value of the thermostat. You can construct correlation-corrected estimators, but this will always assume that your random variable A is in a steady state, which means in this particular case that you would have to remove the warm-up phase from the time series. If we zoom into this graph, we can clearly see that the data points are correlated with each other. In fact, I am sampling way more often than necessary. And this bias will pose a problem when trying to estimate the variance of the mean. You can quantify the correlation in your time series by plotting the autocorrelation function R. In this plot, you can see that the correlation between data points which are n time steps away from each other is decreasing very rapidly. In fact, at around 50 time steps, there is almost no correlation left. It would be very tempting to say that you could simply subsample your time series by a factor of 50, which is to say, only look at data points which are 50 time steps away from each other, and compute the variance of the mean based on that subsample. The problem with this strategy is that you will get a lot less data points, and you will always overestimate the variance of the mean. But you also can't use every single data point, because the bias will lead you to underestimate the variance of the mean. What you need is to construct an estimator of the variance of the mean that uses this autocorrelation function to quantify and subtract the bias. You can reuse the estimator of the mean, but now the correlation-corrected variance of the mean estimator has a different formula. You still have this 1 over n prefactor, but you are now integrating the autocorrelation function between minus tau int and plus tau int. The standard error of the mean is again the square root of that. Estimating tau int is not trivial. The autocorrelation function looks exponential, but in most cases it is not, and you will have to fit some power function to get the asymptote. Tau int characterizes the timescale on which correlation in the data is decaying. You can use it to estimate the effective sample size, which gives you an idea of how many data points in your time series are truly independent. However, again, you cannot simply subsample your time series and only take out nf sample data points, because then you will overestimate the variance of the mean. That's because in this case, the thermostat is using a random number generator to rescale diversities. And so if you take less data points, then each of these data points will be a lot more sensitive to the noise. However, you can use the effective sample size to figure out if you are oversampling. You can never improve the statistics by oversampling. The only way to improve the statistics is to simulate for a longer time. There are other ways to estimate the variance of the mean. One way is called the binning analysis, where you divide your time series into smaller subsets, calculate all these means, and calculate the variance of these means. This was a popular method because it was computationally less demanding than integrating the autocorrelation function. It will also give you results which are very similar. However, to find out the optimal value of k, you still need to fit a power function to a long time tail, which means that it is still less cumbersome. Another method is the jackknife, where you again divide time series into smaller blocks, but this time you compute the means of the time series without each block. In the end, you will get the exact same result as with binning analysis. The jackknife method is more complicated to script, and it's only relevant because it is a special case of the bootstrap method. If you would like to learn more about this formula and how to derive them, please have a look at these two papers by Janke and Weigel.